this one, the incremental picture looks like this. Okay. In terms of the small signal parameters, this is the picture we have. Okay, this is the bulk, drain, gate and source. Now we can choose to either connect the bulk to the source or to ground. If we connect it to source, we found that the small signal gain was Gm by Gm plus GDS plus any load that you may connect. Okay. So V out is here. Okay. And if you incrementally ground the bulk, this is the DC gain. Okay. So when the bulk is connected to source, the DC gain is approximately 1. Okay. And when the bulk is connected to 0, it is quite different from 1 because GMB is quite comparable to GM. Even if GDS and GL are rather small, the bulk transconductance is comparable to the gate transconductance. Okay. So in most technologies, when you make a source follower with an NMOS transistor, you will not get a unity gain. You will get something of the order of 2/3 or 0.8 or something like that. The common drain amplifier is also called a source follower because the source voltage follows the gate voltage. Okay. And for the PMOS, usually you have the freedom to tie the bulk to source. If you really want exact voltage follower or an incremental gain very close to 1, you have to use a PMOS transistor. You use a PMOS transistor with its bulk tied to source. Okay. Any questions on this? So the DC analysis is quite simple. Now, if you, the AC picture can be analyzed by adding all the parasitic capacitors. I will ignore the bulk transconductance, and when it is there, you can add it to GDS. Okay, it always appears in as a conductance in parallel with GDS. Okay. So wherever you have GDS, you can substitute GDS plus GMB and you will get the right expressions. Where do we have the parasitic capacitors? Between gate and source and between source and ground. Also between drain and bulk, but that doesn't matter. Okay. So predominantly there are two capacitors. I will call this CGS, and this represents the source bulk junction capacitance as well as any other capacitance that you explicitly have as a load. Okay. So this is a voltage buffer. You use this to drive either small resistances or large capacitances. Okay. So you can have a case where there is a substantial amount of load capacitance applied to the source follower. Okay. Gate to ground, yeah. So we'll also have this CGD, okay. Now, looking into the source follower, CGD will appear across whatever impedance is provided by the rest of the circuit. It appears directly at the input, right? CGD appears between the input and ground. So I'll remove it from here. I'll analyze the impedance without that. And if I need to include CGD, I can add it in parallel to the calculated impedance. What is the impedance looking in here? So the important thing here is that it looks like a negative resistance. This we analyzed in the first assignment. If you push in a current, there will be a voltage developed with 90 degrees phase lag. Okay. Now, the input current also flows through the load capacitor. Okay. For simplicity, let me even remove GDS. Okay. When we have small GDS, this is a good enough approximation. And the voltage across gate source, which is 90 degrees lagging, minus 90 degrees with respect to the current, causes a current through the transconductance, which is also minus 90 degrees with respect to the input current. So the voltage across the load capacitor, because of this component of current, is 180 degrees behind the input current. Okay. So there is a component of the voltage which is 180 degrees out of phase of the input current, which corresponds to a negative resistance, okay, or negative real part in the input impedance. So the input impedance looks like CGS in series with CL, and a negative frequency dependent negative impedance. This, what is the expression for this? It is this correct? Huh? Sorry, by GM, not GM square, I think. This is the conductance. So the resistance is this correct? Can you verify? This is the resistance value. Okay. This is a frequency dependent negative resistance. So that can cause problems if you have a large source resistance. If you drive it with an ideal voltage source, any impedance is not a problem. Okay. The ideal voltage source will drive whatever current is necessary through this. Now, one of the problems is, for instance, if you have a positive resistance here, and if the negative resistance happens to cancel it exactly, then you could have potential instability problems. Okay. That you have to analyze based on the exact situation you have, because you not only have these parts, but you will also have another capacitance which is CGD in parallel with the entire combination. Okay. And when you include the effect of GDS and GL, the expression becomes more complicated, but you will have one component that corresponds to the frequency dependent negative resistance. Okay. So this can be potentially unstable under certain conditions. If you have a heavy capacitive load, note that it depends on the product of CGS and CL. If either one of them is very small, it's not a big issue. Okay. It's only when both of them have comparable values that you will run into problems. That is, if you have a large device which has a large CGS, you have a large capacitive load, you can have a problem. Okay.
How is the argument of phase shift says that
Yeah, if you have a positive resistance, you push in a current, it develops a voltage which is in phase with the current. If you have a negative resistance, if you push in a current, it will develop a voltage like this, which is 180 degrees phase shifted with respect to the current. Okay? That's what I showed here. Is that explanation clear? So, this current creates a 90 degrees phase shifted voltage across this, which creates a 90 degrees phase shifted current through Gm. That going through another capacitor gives you further 90 degrees phase shift, giving a total of 180 degrees phase shift with respect to the input current. Okay. Now the voltage has other parts also. There is a voltage because this current itself flows through CGS and CL. Okay. So the total voltage is sum of all of them. So that's why you see in the impedance, the series combination of CGS and CL as well as the negative resistance because of the current induced in GM. So from this itself, if CGS or CL is very small, the magnitude of the negative resistance is very large. So the amount of current flowing through that is very small, right, if you apply a given voltage. So that generally has a very small effect. Okay. And maybe a better idea also can be obtained. We saw that again in the first assignment, if you recall, we have, let me reverse these. We have CGS in series with CL, in series with this frequency dependent negative resistance. Okay. This we saw was a parallel combination of CGS in series with CL and a negative capacitance. Okay. And a negative resistance. What was the negative resistance? It was I think that was it. Is that correct? Yeah, I think that was, it was frequency independent, that's what I remember. I think this was the expression for it. And if you look at it again, if either CL by CGS is very large or CGS by CL is very large, this becomes a very large resistance. You have then if you look at it, you have two parallel branches. I don't care about the impedance of this. If the impedance of this is very large, most of the effect is because of this part, right? So if I have some large impedance in series, whether it's negative or positive, the current through that branch will be very small. Okay. So I have parallel combination of two branches. The current through this is very small. The current through this is something. Okay. So if I make this component very large, the current through this becomes insignificant. So again, this also points to the fact that if CL by CGS is a large quantity or a very small quantity, then it's not very significant, the effect of negative resistance. If CL by CGS is comparable to 1, you will have a problem. Okay. No, CL into CGS, I cannot compare it to 1. It is capacitance square. It's the ratio of CL by CGS. You have this expression you must be familiar with, right? You are familiar with things like x plus 1 by x. Where does it have a minimum? 1x is 1. Okay. So same thing here. Okay. And I also had earlier mentioned that you can use this as an oscillator instead of an amplifier, in which case you explicitly connect a capacitance here. The ratio is not always 1, but something close to 1, 2 or 3 or something of the sort. Okay. So you have to do this because in an oscillator, the negative resistance is what you want. Okay. When you want to use it as an amplifier, negative resistance is a nuisance. Whereas when you want an oscillator, that's what you want. You want some source of incremental energy to compensate the loss of the tank circuit you have. So you should maximize this effect, maximize the effect of negative resistance. So you make this ratio close to 1, and that has implications on how easily it oscillates. Okay. So if you make one of them very small compared to the other, it will probably not oscillate. Or you will need a very large GM to make it oscillate. Note that this also depends on the value of GM. If I have a very large GM and a large skew between CL and CGS, you can get the same effect as a small GM and CL by CGS close to 1. Okay. Of course, it is efficient to use a small GM, which means a smaller power dissipation, and a CL by CGS close to 1 when you want to make a negative resistance. Okay. When you want to avoid it, you want to make sure that either the load capacitance is very small or CGS is very small. Okay. And while solving the first assignment, we saw ways to combat this. If the input component of the negative impedance becomes too large, we have different ways of combating it. So I'm not going to go through that again. One was to use this picture and connect a positive impedance branch which cancels out this exactly. Okay. Any questions on the input impedance of the source follower? So a source follower is a useful block because it's a voltage buffer, but it can give you problems especially if you are driving a heavy capacitive load. Okay. Now, one of the things I said was you use a Cmos source follower if you want a gain of 1. Now, you can do this, but a Cmos looks like this. You have an N well on a P substrate and you have P plus diffusions to make the drain and source. Okay. Now, we want a gain of 1, so you will connect the well to the source. So, that means that there is a large junction capacitance between the well and substrate that appears between the source and ground. So, by trying to make a gain close to 1, you are actually adding a large load capacitance. So, that can be a problem again, if you especially at higher frequencies. I mean, there are two problems with higher frequencies. First of all, PMOS has lesser mobility, and secondly, if you try to do this, if you try to connect the source to bulk, it will give you better DC performance, but it increases the load capacitance. Okay. No, it will not affect the DC incremental picture. It will very much affect the AC incremental picture, right? Why would you want to do this? The suggestion is to connect the bulk to the input of the PMOS. First of all, why do you want to do this? Higher gain. Higher gain it might give you. But the one problem with doing this is that you will have forward bias. Okay. So, you can have forward bias with this, right? Because this is P plus and this is N. Now, this voltage is positive. So, you can have forward bias of the junction. But there are actually circuits like this which apply input to this also. When this voltage becomes very small, there are many things that happen when you try to lower the bulk potential in a PMOS, or for instance, let's say I start with this. Let me go to a new page. Let's say I start with NMOS, and for now I'll assume that I have freedom to tie the bulk anywhere I want. I have the bulk tied to 0 volts, and then I have another scenario where I have the bulk tied to a negative voltage, or thirdly, I have the bulk tied to a positive voltage. Okay. So, what's the difference between these three as far as the threshold of the MOSFET is concerned? So, if this is VT0, what will be the threshold here? It will be more. So, it will be VT0 plus something. Here it will be VT0 minus something. Now, the risk of course is that you have a diode like this which may get forward biased. But if you lift it up only by let's say 0.1 or 0.2 volts, you will get a reduction in threshold voltage without the forward bias current being significant. So, it is used sometimes to reduce the threshold voltage. Now, because the threshold voltage is reduced, the VGS for a given current is also smaller. So you can in fact tie this here and use it in some applications. But you have to make sure that this voltage will not be more than about 0.2, 0.3 is probably maximum. Beyond that, it will start conducting substantially. Okay.
So we are to some extent lowering the input impedance also.
That is because of leakage. I mean, if the leakage is insignificant, that's not true, right? So if you are, see, the characteristics of the diode is an exponential. Okay. So if you are operating somewhere here, it may be okay. If you are operating here, it's not okay. But that's true. I mean, whenever you do this, you always have a risk of forward bias. You can use it only when you know for sure that you will not forward bias it. And actually, there are many interesting circuits that have been made using this, using the bulk also as an input terminal. As I said, small signal wise, there is no difference between bulk and gate. You can apply it from the bulk or from the gate. Just so happens that the transconductance from the oxide gate is more than the transconductance from the back gate. Okay, it is designed that way typically. Now, when you want especially low voltages, you want lower threshold voltages also. So it's in those conditions that you try to do this. So if you look at one of the papers in the International Solid State Circuits Conference a few years back, normally you make a Cmos inverter like this. Okay. What is the minimum supply voltage needed to operate this? VTN plus VTP, right? So otherwise, like both of them will be off in some, when the input is some intermediate voltage, and that's not desirable because the output will be floating in that case. So, and to complete the picture, I'll have the bulk of the PMOS to VDD and the bulk of the NMOS to ground. Okay. Now I have to lower this. Let's say I want to operate with a VDD of half a volt. I can't do this. If my VTN and VTP are, let's say, 0.5 or 0.6 volts, I can't operate with half a volt supply. So you can instead do this. You connect this to ground and this to VDD instead. Okay. So now what happens is that the threshold voltage of the VBS of the NMOS transistor is positive, equal to VDD, and VBS of the PMOS transistor is negative and also equals VDD. So you clearly cannot use it for VDD greater than about 0.3 or 0.4 volts, okay, or maybe half a volt at most, but it will lower the threshold voltages. Okay, so you can use this with very small VDD. In fact, you can't use it with high VDD. Beyond 0.6 volts, you cannot use it. But it's an interesting circuit. Looks like a typo. So you connect the bulks opposite to what you normally connect them to. Okay. And this is a digital circuit. There have been op-amps also made for 0.5 volt supply operation in the same technology that you are using to simulate. Okay. If you do conventional circuitry, I don't think you will be able to make circuits with 0.5 volt supply in your 0.18 micron technology, whereas there are op-amps that are made by using the bulk also as an input terminal. Okay. Any questions? Not yet. This one was published by Intel. Maybe they are using it inside somewhere. Intel inside, right? And the other, I mean, it's not yet done, but usually there is a lag between when you publish the circuit and when it's actually used. And during that time, of course, people also look at whether it's practical or not. I mean, another way of getting circuits to operate at low voltage is to make low threshold voltage transistors. Okay. But one of the problems is always that if you make a very low threshold voltage, you can turn it on, but you can't turn it off easily. So I think only after all that is worked out will it be used. But I mean, it's probably used in some limited extent somewhere. Okay. So that's actually good for analog circuits. In analog, you don't care about turning off things, right? So there should be fewer restrictions. of doing this type of things for analog. And also there is another thing. If you have gone through basic digital course. So do you know what latch-up is? So latch-up happens because of forward bias junctions in the substrate, right? So there is another risk also. Now with modern technology where you isolate the different transistors differently, they say that there is not much risk of latch-up. Now the doping of the substrate has been increasing to reduce the risk of latch-up. Okay. When you increase the doping of the substrate, there will be very little voltage drop across different points in the substrate. So what happens with latch-up is you will get a positive feedback structure like this. Okay. So if some junction gets forward biased, then it can become a latch. That was the original CMOS latch-up. Okay. So when you have NMOS transistor and PMOS transistor, let me see, this is an NMOS, this is an NPN, and the PNP is here, okay, and you can have let's see, this connected to this. When you have a CMOS inverter, this is what happens, right? The drain of this transistor is connected to this one, but there are also these parasitic junctions, okay. If you have a large drop across this, let's say this is grounded, then this will get forward biased and that will turn the latch on. That's why as you go to newer and newer technologies, you have smaller and smaller components, but you also have higher and higher doping in the substrate so that this won't happen. Okay. So when you deliberately forward bias junctions that are not supposed to be forward biased, it could potentially lead to latch up. So only after all those reliability issues are addressed will you get these things in practice. Yeah, so right now the present way of isolating is not by just putting them all on a common substrate. There is some oxide between the NMOS and PMOS transistors. So the risk of latch-up is a lot smaller in modern technology anyway. So maybe it will be used. I don't know. Okay. So anyway, this half-volt op-amp was, this group in Columbia has made a lot of half-volt circuits, and this half-volt op-amp and many other circuits with this was done by Shauri Chatterjee, who was an alumnus here. He graduated in 2000. Now he is a prof in IIT Delhi. Okay. So you can write to him if you want to. He also has a funny homepage if you want to look at it. Okay. No, if you have 0.5 volt supply, that's it. You are limited to that one. So, in fact, see the half volt circuits that have been built so far, they are not very power efficient. They take lots of current. So what the op-amp you can make with 1.8 volts, you compare it to half a volt, the total power consumed by half a volt circuit is a lot more. That's because you need lots of other bias branches and other things. And with a half volt supply, you can only expect a swing of the order of half a volt. Okay. So that is always a problem. But the thing is, one of the things that would drive people to make something like this is that when you scale the technology and go to lower power supply, the advantages for digital are very obvious. First of all, you scale the technology so circuits become smaller, and also you shrink the voltage. The power dissipation, which is dependent on the square of the voltage, and also the capacitance will go down, okay, proportionately to the scaling of the power supply. Whereas for analog, it's not very obvious. Okay, the point of making a half volt op-amp is, let's say you have half volt digital technology. The fact that you can make any analog circuit at all in half volt is a big deal. Okay, it's not that it's necessarily better; it may be worse. In fact, it's been shown that if you want the same functionality with the same specification, that is the same SNR, in a high voltage technology and a low voltage technology. In a low voltage technology, you may end up burning more power. Okay, that's always possible. But at half volt, without even looking at how much power you burn for a given signal to noise ratio, the bigger question is whether you can make any circuits at all. Okay, So, if you can make any circuits at all, it may be useful. That's the idea behind investigating circuits like that. Now, of course, as you scale the technology to very low voltages, it looks like even for digital there is a problem because of leakage, etc. But clearly the advantage for digital with scaling up technology is far more obvious than that for analog. Okay. But of course, I think we will find a way to live. That's why you are here. So, my profs used to say that when they started designing in 5 volt technologies, people who had designed in 10 volt technologies used to tell them you'll never get enough signal to noise ratio, you'll never be able to do any analog circuits with this. So 3 volts looks like a very high voltage now. So maybe we'll find some way to do it in half volt also. Or no voltage at all. Okay. I mean, this always has been a question. I mean, if you look at the conference papers, or usually there used to be a panel discussion in every conference, starting from old days when you had like plus minus 15 volt op amps, that voltages are shrinking, what do you do? Well, there is all sorts of panic, but then finally you find some way. Now 1.8 volt looks quite normal, I think. Right? So I think even if you look at papers about 15 years ago, they were published with 18 volts or something like that. So 15, 20 years back. We do make progress, we do manage, that's why I have a job, and hopefully you will have a job also and keep it for a long enough time. So that's about we got into all this through the discussion on the common drain amplifier. So one more interesting thing about the common drain amplifier is its output impedance, and in fact that's the only thing that we had left to analyze. So first of all, what is the DC output impedance of the common drain amplifier? What is R out? So if you have plus just GDS, it will be these two, and you can also have GMB if the bulk is not connected to the source. The output of a common drain amplifier is the input of a common gate amplifier, right? The circuit looks exactly the same. When I am analyzing the output impedance of a common drain amplifier, I have incrementally grounded this and this. I have exactly the same situation when I am analyzing the input impedance of a common gate amplifier. So the results are exactly the same. So the output impedance is better because of GMB, just like the input impedance of a common gate amplifier is better because of GMB. Okay. Now, what happens to AC output impedance? Huh? So if we just have this, okay, maybe I'll redraw this whole thing. Let's imagine a scenario where the common drain amplifier is driven from an ideal voltage source, and we have capacitance here and a capacitance here, okay, and also a capacitance here. Let me ignore this, okay, I'll just look into this part of it. Okay, this I think of as a load capacitance, right, that I connect. I want to look at the transistor. So the incremental circuit looks like this. And I have the CGS of the MOS transistor. I have excluded the load from this, okay. So what is the input impedance now? What is the output impedance now? It's the output conductance we had before plus the admittance of the capacitor, okay. Realistically, you will not drive it with an ideal voltage source, okay. So let's say it has some source resistance. What is the output impedance now? Have you seen this circuit? Where? This was also in the first assignment. So first assignment contains answers to everything. That's the bottom line. Okay. So what's the output impedance? What's special about it? Do you remember what the answer was? So it looks like an inductance. Okay. Why does it look like an inductance? Again, let me remove this GDS. GDS appears in parallel. If I want to, I can include it in parallel with the entire thing. Why does it look like an inductance? Of course, if you do the small signal analysis, linear analysis of the circuit, you do get an inductive part. Okay. What is the impedance at very low frequencies? One over Gm, right? It's R out. What is the impedance at very high frequencies? What is the impedance at very high frequencies? So it is 1 over Gm contributed by the transconductance in parallel with Rs. The Cgs is shorted. Actually Gm is not there, sorry. Cgs is shorted, so the voltage across that is 0. So the Gm part is disabled. It's only 1 over Rs, or Rs is the output impedance. Okay? And we assume that Rs is much more than 1 by Gm. So there is a region of frequencies where the impedance increases. Okay? And that is the inductive part. Looking at the circuit, can you say why it behaves like an inductor? Yeah. So it's better to drive it with a voltage source, right? Or you push in a current, where will it go? Will it go into the Gm or the capacitor? What is the, I mean, even more intuitively, can you describe why this is an inductor? Here. Oh, from here. But that's not what we are analyzing, right? We are looking at the current response to this one. But what you say is true roughly. I mean, if you apply a voltage here, the voltage across this is 90 degrees out of phase in under some conditions, and that gives you a 90 degrees out of phase current. That's correct. What is the very first description of capacitor and inductor you heard?
Yeah, actually here you are converting the applied voltage in place converted 90 degree to current, and that is again due to the Gm thing. It is if you apply current, it has a 90 degree out of phase in the capacitor voltage, which is taken as Gm as the current. Looking into that, this axis, the current is being 90 degree.
No, that's correct. That's correct. But first of all, if you start off with a current, you start with the current here. Okay. For the output impedance, what matters is the total current. Okay, or at least the current through this part. For to establish the output impedance, what you have to establish is that the current lags the voltage here. Okay, not necessarily just the voltage across the capacitor. Not necessarily the current through the capacitor. What you are saying is this: the current through Gm lags the current through the capacitor. Okay. But I mean, it's all in the right direction. But let's say even without using phasors, etc., what is the first thing you hear about inductor and capacitor? Long back, when you first hear of an inductor. No, even before that, I think. The capacitor holds what? Voltage. I mean, you hear that the capacitor voltage cannot change instantaneously. Similarly, an inductor current cannot change instantaneously, because a back EMF is developed that will resist the change in flux. Okay. So what happens if you, let's say you have a certain current flowing through this. Okay. And then you apply a step voltage. What happens to the voltage across the capacitor? Doesn't change immediately, right? So what happens to the current through Gm? Also doesn't change. So because the voltage across the capacitor is held in response to a step, the current through the Gm is also held. Okay? Exactly like in an inductor. What happens if you do this? If you step the voltage across an inductor, it will still hold the current. After a while it will change. Okay? Similarly here, a step voltage here will not change this. What will happen if you apply a step here? Initially you will see a step here also at the gate. Eventually, of course, it will reach steady state and come to 0. So similarly, if you look at the current through this, it will stay constant at its value and then slowly decay. Okay. So the action of the capacitor holding its voltage causes the action of inductor current being constant for a while. So that is also some intuitive explanation of why it behaves like an inductor. Okay. So that's about the common drain amplifier. Okay. Now we saw that the input impedance looks like a negative resistance, and the output impedance looks like an inductance. So sometimes to buffer very heavy loads, you may have two voltage followers. Okay. So this kind of thing can be disastrous. Right? This is used with proper care. You can use this, but now you have an inductor looking here and the negative resistance looking in here. So you can make a nice oscillator like this. Also. Okay. So if you cascade a number of voltage followers, it should just give you a gain of 1, but that's not all that happens. You can have oscillations because of this. And even if it doesn't sustain the oscillation, in response to a step, it can ring a lot. You can try this out and see. So is the operation of the common drain amplifier clear? Again, we have only stuck to the incremental picture. We will see how to make the total thing. We are already discussing the bias circuits. We can combine the techniques of biasing with applying signals in the proper way to get whatever result we want. Any questions on the small signal analysis of the source follower? Any other general questions on biasing? The other day we started off with discussing the biasing stuff. I don't know if we should continue it now. So if you have any questions on anything, we can discuss it instead of going to a new topic at this time. Okay, since you are not asking questions, I will ask you one. Let's assume just a Cts and Gm model for the transistor. Okay. Looking here, it looks like an inductor. And in fact, this is also used in some cases where you want an inductor. Okay. If you want to wind an inductor, first of all, you can wind very small values of the order of 10 nanohenries or so on a chip. But if you use this inductor, the value is related to Gm and Cgs. By changing the bias, you can potentially change the inductance value. So in some places where you want inductors, but the signal swing is small enough so that the small signal analysis is valid, you can use this inductor. Okay. It depends on how accurately you fix Gm and Cgs. So if Gm varies and Cgs varies, RS also, right? It depends on all three of them, in fact. What was the inductance value? So the dimensions of inductance are capacitance times resistance square. I think there is only one way you can combine the three of them to. I think it is C times Rs divided by Gm. Okay. So it depends on, if you have variations in Cgs, Rs and Gm, it will vary the amount of inductance. Now, you either have to bias them so that the variation is small, or you have to live with variations. Okay, those are the only two things that you can do. Yeah. Yeah. Yeah, that's correct. So actually, if you remember, the output impedance is, so the part that is through Gm, in fact, if you look at it, the voltage across the capacitor does this, right? If you apply a step, it will slowly change like this. So that means the current through the Gm part changes like this. So that is equivalent to an L and R in series. Okay. Now, whatever current you have here is represented by Cgs and Rs. Okay. So this is the effective input impedance of the output impedance of the source follower. We discussed this also, right? Why this is not a second order system? Why is it? Why is this not a second order system? So the time constant of this branch happens to be exactly equal to the time constant of this branch. Okay. So that's true. The inductor description holds only to the current that is flowing through Gm. Anyway, we evaluated the output impedance and said that it goes from 1 by Gm to Rs. Okay. Now we ignored this parasitic capacitance, CGD. What happens because of it? Will it change the circuit in any fundamental way? Will you still get the inductance? You get the resistance part only. Yeah. So, what happens? So, what do you think will happen? I mean, what happens at high frequencies or low frequencies or any other frequency? Inductance value will decrease. Why?
Let's say we are applying a step input at the step at the output. In that case, whatever like capacity division.
Yeah. So that is one of the things that happens. The voltage at the gate is not exactly equal to the voltage at the source. It will be a divided version. Okay. So if CGD is much smaller than CGS, it will still give you approximately the same inductance. Otherwise, it will give you a divided part. Okay. I think that is true. Yeah. What else happens? When analyzing circuits like this, you have to assume that there are distinct ranges of frequencies where one or the other component is significant. Now, that may not be true in practice. Okay. It may not happen that way. Then you evaluate it and see if it's true or not. So, let's assume that CGD is smaller than CGS, which is quite reasonable. We can assume that it is quite a bit smaller. Okay. What happens to the impedance at very high frequencies? Huh? 0. Why? Oh, okay. When the capacitance becomes a short. When the capacitance itself is not a short, but will you still get RS? You will get 1 by Gm. See, essentially, previously, the voltage across this capacitor went to 0 at high frequencies. Now, even at the highest of frequencies, you have a capacitive divider. So, you have a part of Gm still contributing to the impedance. Okay. So, the highest impedance will be what? Highest impedance looking into this one. Okay. Forget what you see into this branch. Looking into this part. What is the highest impedance you see? It's this capacitive divider times 1 over Gm. CGS by CGS plus CGD times 1 over Gm, which can be smaller than RS. It could be larger also, I don't know. Obviously, if CGD is very small, is this correct? Yeah, so, okay, so it will be, so what happens is, if this quantity happens to be smaller than RS, the range over which you get the inductive component is reduced, right? That is one of the things that happens. So you can imagine a range of frequencies where the impedance of this is much higher than the impedance of RS. Okay. Impedance of CGD is much more than the impedance of RS. Then it behaves like, exactly like what we described before. You can neglect this and you analyze. Then there comes a range of frequencies where this is significant. Okay. Then you can't neglect it anymore. Okay. So you will have a smaller range of inductive behavior. That's one of the things that happens. Of course, the total impedance is the parallel combination of this and this. What you see inside this also changes. Okay. So in fact, if you look at it, the plot I drew even for the earlier case was, for the earlier case was like this. Okay. The part through GM does this. It always goes on increasing. Okay. And the part through the other branch, the passive branch, is like this. Okay. So this is due to GM and this is due to CGS and RS. Okay. So, and the net impedance is the parallel combination of the two. So on a border plot, you can approximate the parallel combination by the smaller of the impedances. Okay. So you will get something like this. Right. What happens now? In this case, the part through GM itself does something like this. It starts from 1 over GM and goes to the capacitive ratio times 1 over GM. Okay. Isn't it? This is if you plot the impedance of the GM part of it, this is what you see. And what is the impedance of the remaining part? This one. Yeah. Actually, I made a mistake here. This is not 1 over RS throughout. It is something very high at low frequencies and then it does this. Okay. In fact, this pole is exactly the same as the other one. It does this. So in this particular case, what happens is that you will have something like this and you can have something going down. Okay. So the net impedance, if you see, it will do something like this. Now depending on where this pole is, the inductance range can be very small. It can be too small to be useful. Okay. So without CGD, you get a nice inductance which you can potentially use. With CGD, the range is certainly reduced. Okay. And the range is related to how much CGD is compared to CGS. Okay. Is this okay? So you can use this as an active inductor, but with CGD you have to carefully adjust the parameters so that you do get inductive behavior in the range of frequencies you are interested in.
So when we have this CGD, the effective GM is actually decreased, right?
Effective GM. Yeah.
So basically 1 by GM should increase.
No, effective GM? No. At low frequencies it's not, it doesn't have any effect, right? Because at very low frequencies, this point is at 0 volts because of the resistance. So the entire applied voltage appears across this.
So at high frequencies,
Yeah.
when we are having this capacitive division,
Yeah.
basically the voltage that is
Yeah, that is represented by this part of it. Okay. So that's why I said the range, whatever you do, cannot be more than this. Okay, of inductive behavior. Regardless of what this does. This can only make it smaller. Okay. So, and this range depends on the ratio of CGS by CGD. CGS by CGD is very large, it will be large. If CGS by CGD is very small, you will just have something like this. In this case, the impedance is second order. It's not a first order impedance. Okay. You get the same result? You are looking at, now this is the input and this is the output. Is that how you are treating the amplifier? Or? So, now again, see, if you try to use Miller's theorem, this side it has only passive components. So the voltage V0, if you think of it as an amplifier from this Vi to this V0 and connect a capacitor across it, this transfer function depends quite a lot on CGS. Okay, so you can't remove it, evaluate the gain and put it back and see. What's that? Shouldn't there be a 0 in the impedance or? Yeah, there is, right? Yeah, that's correct. Yeah. So there will be, it will have 1 0 and 2 poles, right? Sure. Yeah, that's right. So, I mean, I think the case you are referring to will happen if CGD is much larger than this, then they will be of the same order, isn't it? Yeah. So, in that case, yeah, you will not get a significant region where you have inductance. Anything else?